What's up guys, Major Math with another video on fluid mechanics. If you have any questions, drop it in the comments, and if you're having trouble with other problems, I've attached my email in the description, so please feel free to reach out. Without further ado, let's get started. Question 3.3, or example 3.3 in the textbook, says oil with a specific gravity of 0.8 forms a layer 0.9 meters deep in the open tank that is otherwise filled with water at 10 degrees Celsius. The total depth of the water and oil is 3 meters. What is the gauge pressure at the bottom of the tank? Okay, in this diagram they gave us in the textbook, they've already labeled these, which will be useful later, and they gave us our heights, temperature. So let's figure out our goal here. So our goal is, what is the gauge pressure at the bottom of the tank? So find pressure at 3, right? The pressure right here at the bottom. We're given, well, the only given we need to write that's not on the diagram is specific gravity of oil equals 0.8. Okay. So let's go ahead and we're gonna need the specific weight. So let's go ahead and do that real quick. So specific weight of oil, or I'll show you what the specific gravity formula is. So specific gravity is equal to specific weight of the given liquid over the specific weight of water at a temperature of 4 degrees Celsius. This, if you look in the textbook, that equals, let's rearrange it, but I'll tell you what it equals in a second. So if we're solving for the specific weight, in this case it's oil, that will equal the specific gravity, and then the value at the textbook of water at 4 degrees Celsius is 9,810 newtons per meter cubed, right? And then it's giving us that the specific gravity is 0.8, so let's go ahead and plug that in, and then that gives us a value of 7,848 newtons per meter cubed. That's a 3. So that's what the specific weight of oil is. Alright, to find this, we are going to use the hydrostatic equation. Pretty big equation in fluids that will be built upon throughout the course. The hydrostatic equation, there's some different forms of it. But the form we are going to be using is the one that looks like this. Is pressure 1 over specific gravity plus z is for height in this case equals pressure 0.2 over specific weight plus the height or depth at 0.2. So we know that the specific weight, we're in the first, from 1 to 2, it is oil, right? So to do this, we know that it's talking about, what's the gauge pressure, right? So we know that the pressure of 1 is 0, right? Because it is exposed to the atmosphere. So the gauge pressure is 0, but the absolute pressure would be the atmospheric pressure. But it's asking for the gauge, so we know that this is just going to be 0, right? That is just 0, and then you're left with Z1 equals, and we're in oil, so O for oil. And then we have the height, the depth at pressure at 0.2. We can rearrange this some more to, because we're going to try, what we're trying to do here is find the pressure at 0.2, and then once we find the pressure at 0.2, we can actually find the pressure at 0.3. So we're solving for pressure here. Rearrange this, say Z1 minus Z2 equals, and we'll go ahead and multiply it by that specific weight, equals pressure 2. Right? Just did some rearranging. The difference between the heights of 0.1 and 0.2 is that 0.9 meters. So let's go ahead and plug that in. And then we found the specific weight of oil as 7848 newtons per meter cubed. And multiply that together, that will actually give us our pressure of 0.2, which if you put that in the calculator is, let's see, the pressure is 7063.2 newtons per meter squared. So now we're going to have to do the hydrostatic equation again to find the pressure at the bottom where pressure 0.3 is. So we're just going to rewrite it, say same equation. This time we're in water, so I'm going to put W for water plus the height at Z2 equals, at least imagine, equals the pressure at 0.3 over specific weight at water. So that's what we're in now, plus the height at 0.3. So do more rearranging to get P3 by itself. So we get, do some algebra here. If you do some algebra, you get that P3 equals P2 plus specific weight of water, and then 0.2 minus. So that's after doing some algebra, some rearranging. And then if you plug in our known values, so we just solved for pressure 2, right? So let's say that P3 equals 706 3.2 newtons per meter squared. And then you add, I didn't say what this was yet. If you look in the textbook, at water at a temperature of 10 degrees Celsius is 9,810 newtons per meter cubed. And then the differences in height between 0.2 and 0.3 is 2.10, 2.1 meters. Put that in your calculator, you will get that the pressure at 0.3 is equal to 27,644 newtons per meter squared. And then we know that newtons per meter squared is the same thing as pascals, right? So that's our answer. If we think about this a little bit more, so this makes a lot of sense, right? Because I think we've talked about in other videos, right, that pressure is equal to a force over area, right? And in this case, the only force is weight, right? It's just the weight of this liquid of oil building on top of the water, and then within the water, just all the weight adding up, compounding to get to the very bottom, and that's why the pressure is the most at the bottom, right? So the only force acting in this case is the weight of the water or the oil itself just compounding onto each other. So we know that the force of weight is mass times gravity. And then if we rearrange that some more, we know that we can rearrange this, say that mass equals the volume times specific weight times gravity. Not specific weight, sorry, density. Jumped ahead of myself. Okay. Rearrange it some more. We know that density times gravity is the same thing as specific weight. And then we know that volume can be arranged to area times height. So area times height, and then specific weight over area. Areas cancel out. You get, and I should have wrote a z here. H is for height in this case. So then we get pressure is equal to height times specific weight when you're just dealing with the force of weight of the liquids just building up on top of each other. So we know this, right? And then if we look at what we did here, we kind of took the long way here using the hydrostatic equation. But all we did here is we took the pressure at point 2, right? So we solved for that earlier, 7,063.2. So we just took that weight from that pressure at this point, and then all we did was just add the pressure. We just added this right here, this height times specific weight. So that's specific weight, and that's the height. So we kind of took the long way, just for lesson purposes, but you can also just, that's a faster way of doing it. Thanks for watching, soldiers. Don't forget to leave a like and subscribe for more content like this. If you have any questions, leave it on the comments, and if you need help with any other problems, feel free to contact me with the email shown on the screen.